So we all know the Euler-Lagrange equation. The Euler-Lagrange equation applies when we're trying to minimize some integral of the function f, and we just use the one variable version, y dot, and x. This equation, the Euler-Lagrange equation, tends to give you a second order differential equation, which is somewhat challenging to solve in some cases. It's a lot easier if this f does not depend on x. If that f does not depend on x, then there's a shortcut, and I can best explain the shortcut by working backwards. Let's try and calculate how this thing here, how that behaves. Now if we can expand this out, we use the product rule, and then we get the derivative of this, remembering that this is a function of y dot, and x, so we're going to get three terms. We're going to get the dependence where y dot depends on x, we're going to get the term where y depends on x, and we're going to get the very explicit dependence of f with respect to x. Now in the situation where this term here is 0, i.e. f does not depend on x, then we can make a simplification. We can make an immediate simplification, of course, because this term here cancels with that term there because they are equal and opposite. And the final two terms we can look at a little bit more carefully because this one here, this bit here, that's very familiar. d dx is exactly that bit there. So of course this bit here is just equal to this. So we're going to get a y dot delta f delta y minus exactly the same thing. So those two also cancel. So in other words, using the Euler-Lagrange equation and the fact that df does not explicitly depend on x means we get that this thing here is constant. And the nice thing about this is that this is a first order differential equation typically. And that has a name. It comes up so often that it has a name. It's called the Beltrami identity, and we're going to use it many times. In fact, I just proved it for the single variable version. If we have the multiple variable version, then everything is very, very similar, of course. What we have is an Euler-Lagrange equation for each variable. So we're going to have a set of Euler-Lagrange equations. This is going to be a vector. This is now going to be a dot product. Here we're going to have a whole sum of terms. And so down below we'd have the sum over j of all of these terms, and each of those are individually 0, so that still sums up to 0. And so that dot producted term in the brackets is constant, and so we have the multivariable version of the Beltrami identity.